Okay, get started. First, let me make an announcement. It's not showing on the calendar yet, but this coming Friday, Philip Hieronymy will speak instead of me. We're swapping some Fridays because I'll be out of town this coming Friday, and then he had a problem the Friday after that. So this coming Friday, Philip H. will speak in my slot. Oh, online or is he here? I can't remember now. I thought he said he was, well, I guess, okay, online maybe? Okay. Anyway, all right. So he's going to be here instead of me, and then I'll be back online the week after that because I will still be out of town. The other thing I want to say is that I posted some more stuff on my resource page. Posted more stuff. This has to do with what it'll be related to some of what I'm going to talk about today on my resource page for the course. All right, so some of the stuff I mentioned today hasn't been there, and then I realized I should put it up there. So I have a little sort of backfill, I guess, to take care of here on some stuff. It's worth mentioning though. Actually, yeah. So maybe I'll just leave this up here for now. Go over here. So there's been a lot of these questions about, when can you get the whole flow and when can you get all trajectories as a definable family of things. And so let me just sort of point something out here. It's not hard, but it's useful to know that if we just take the field of reals and one of these log spirals, this actually defines the whole flow of the vector field from whence it came, which we were calling F omega. And of course, I should say, and all trajectories show up as a definable, are obtained as a definable family. So as we were talking about, okay, as long as you've got restricted exponent, restricted sign, then you have the restrictions of this exponential map that show up for matrices. And so as long as you have those around, you always have partial flows and all trajectories of bounded stuff pervade, on any large enough box or whatever. But here we actually get everything. And it's actually pretty easy to see, but there's a key trick here. It's not hard, but it's a crucial observation. So let's just remember how I probably wrote this guy down originally as the definition. And yes, for logicians, yes, means the parentheses go there. But I'm not going to say that every time. All right, so I might have defined it this way. Of course, you might look at it now and say, well, why is it a logarithmic spiral? That's why don't you call it an exponential spiral? The point here is that the natural parameterization for this is in terms of distance from the origin. So we can certainly reparameterize this and get the same object. And now it's going to be t cosine, well, omega log t, which I just as soon write this way. And I actually kind of, in the papers, I actually just declare a new operator, function name coslog and sine log because there's so many often. Now I'm going to always be using these compositions. And so we have this. So we can just reparameterize and get it looking this way. Now, one of the advantages is that, of course, if we look at it this way, then for given any positive real number, there's a unique point on the spiral that has that distance to the origin. So in fact, we can definably parameterize the spiral by distance to the origin. But that means, I can do this definably. So of course, then I can get rid of this, which means that that the spiral defines, let's just say sine of log of t omega on all of here, and of course cosine as well. All right, so now we're not talking about restricted anything. This is full on. That function is now definable in the structure. So that means, so in fact, not only do we have the spiral here, we actually have, we don't just have it as the image of a solution, we literally have the solution as well. There it is. So a lot of times, remember, I've been being careful to say that trajectories are images of solutions. You might not have a solution that gives it, but here we have it, and it's total. It's everywhere. And the other thing, so now how do we we certainly have the whole log spiral, and of course we also have so the log spiral is a maximal trajectory of the vector field. That's pretty easy to see. There's another maximal trajectory that, of course, we always have, and that's the origin. So we don't have to worry about that one. That'll always be in a definable family. And so the way to always understand this thing, at least this is my point of view, came to it, is that this f omega, I mean, we're thinking about this as a map from r squared to r squared, but it's really it's really left complex multiplication by this. So it's a complex scalar is really the easiest way to think about this. It also explains why this is a trajectory, immediately explains why this is a trajectory of the vector field. And so once we realize this, we look at this, and now we understand that the other maximal trajectories are all complex scalar multiples of the log spiral, including 0, by the way. There's another complex number, and complex multiplication is a semi-algebraic thing. So we know we can uniformly define that. So now we can uniformly define all of the maximal trajectories. And then all the other ones show up because we have this nice regularity. We're parameterized by distance to the origin, and that's injective, right? So what are the other trajectories that might be around there? Well, of course, I could take it all the way out from somewhere. That's just everything beyond some distance. But in order to get any of the other ones, I really just kind of have to take, if I say I wanted to get this one, like something like that, well, I can just cut it like this. Actually, the better way to do it is to think about the spiral. These, of course, be they're logarithmic. My scale is not very good, right? But if I look at annuli and let those intersect with the spiral, whether it's, I could say, closed here, open here, closed, whatever, intersecting with this will give me bounded, will give me the bounded trajectories. Doesn't matter how big. So they all will show up as a definable family, and the whole flow of the vector field is definable. Okay, so it's certainly possible that this can happen without without, you know, without things being bounded. There's no restriction here. Now, of course, there's another setting where we always can define the flow, and that's if we define the integers, because then we define all Borel sets, and that's so there you go. You can always define everything there. That's not very interesting, but this is useful, and it also it's also going to come up again later on in the talk. This importance of I don't know of any particular name for this, but you know, this injectivity of the distance to the origin, allowing us to really define the oscillation, if you will, the angle that's going to come up. And we can't, you know, I mean, trajectories could be wobbling all over the place, though, and doing all kinds of wacky stuff, you know, and so it's not like this easy trick is always guaranteed. But I know, one of the things I know, that if I have a nice regular trajectory like this, regular is being used too much. If the distance to the origin is injective, at least in a neighborhood of a singular point or something like that, then there's a lot I can do. So if it's at all reasonable, then I have some results in this papers that are posted here that are a little annoying to state completely, but they will reinforce this idea that you pretty much have to look like a log. You will certainly have to define a log spiral, and then, well, there's some other issues about going the other way. Okay, so by the way, so yeah, so I say this explains this explains everything as far as I'm concerned about this about this vector field. Okay. Oh, there's a remark I want to make here while I'm at it. By a former student of mine. It's a reasonable question. The log spiral itself is not definable just from its intersection with the x-axis. So remember, this m omega was just my notation for the intersection of the spiral with the positive real axis. It's not actually definable, so we actually need, in this case, to reconstruct the spiral, we actually need restriction of one of these things or something to an appropriate interval where things are defined, to a compact interval or something, say 1 to 2 or something. Need, say, restricted sine log t omega. I don't know. Say on, I don't know. You pick 1 to 2 is still, yeah.
Did you just prove it actually?
Hmm?
Didn't you just prove it because you showed that you can recover it in the structure?
No, no, no. Here, in here, I can get this. In here, I can get this. I can trivially get the intersection with the positive real axis.
No, but the fact that you need that, you show that it's provable there. So if you had that W, but you're saying that you cannot define sine log t
In here,
inside.
you can't even get a restriction of it in here, because then you could get everything.
All right.
And basically, this was an elaboration or a variation on some of Bianconi's arguments about why you can't get restricted sign from exponentiation and vice versa. So it's actually, you think, well, it actually takes a bit of work to show this, so I'm glad somebody did it, but it's because it's an obvious question to ask. So we do need these, but now remember, when we're going back to the setting of this Tame control theory, I'm always assuming that we have at least restricted x and restricted sign. So then we will certainly be getting this guy too. We'll get this restriction from there, because again, it's restrictions of this are you can get them from the compact trajectories of the spiral. Okay, so that's a good thing to know. Okay, so now I'm going to go back to where we were before. So so until further notice, this guy is just going to be it's going to be an expansion of our bar until I say so. Until I say otherwise, nothing else. It's just what I need. I need to have a name for things. So I guess I'm going to now maybe I'll take this guy. So there's a nice little trick. It's in this one of these papers of mine. I don't claim that this is original to me. I know I just had to write it down carefully. So there's this thing I call AEG for short, which is asymptotic expansion of groups. It's a lot easier to say AEG. Asymptotic, what is it I call it? I can't remember even now what the words are. Asymptotic extraction. Ah, that's what it is. And so this is a pretty easy little thing to do. It's handy. I'm going to state the multiplicative version of this first. So if R defines, and let me say this in parentheses, at least for now, the range of a sequence, because what does it mean to say to define a sequence? That really would mean also with the indexing, I suppose. But I mean the set of all the values. And these will be real numbers with some appropriate assumptions on them that will come up here and we'll see, such that, so a sub k plus 1 over a sub k goes to some alpha that's a positive real number. All right, so right here, of course, what this means is that from some point on, all of these guys should be non-zero and so on. All right, so what I mean by the range of this would be the set, let's give it a name, I guess. The range is just all the values. K and n, all right, because this is indexed by the natural numbers at this point. So there's the range of the sequence. So this is really the set I'm talking about. And of course, once it's collapsed there, we might as well assume that this thing's going to be injective because values will be squashed and things. All right, but it's just too much trouble to say range of a sequence all the time. So if we have this happening, then my structure defines the group. This group alpha z, which is what we call is all of the integer powers of alpha. It's the cyclic group generated by alpha. Of course, I only need the positive ones or the negative ones or whatever like that because of definability, but that's okay. Now, so this is pretty easy. Right. Now I go to this board. So let's just notice one thing. Of course, if alpha is 1, then the result is utterly trivial because then, of course, the group is just the set containing 1. So if it goes to 1, this says nothing. However, because this is easy, there's a harder result if it goes to 1 that's due to Philip. And of course, the converse to this is also obvious. Of course, if I do define this guy, then when I go out to plus infinity, I'll get the the sequence or the range of the sequence, and the successor over the predecessor is certainly going to be equal to alpha each time, right? So this is an if and only if statement, but this is the part that's interesting. There's an additive version here as well that we can use. We probably will at some point. It's not hard to imagine what it's going to be. In this case, we would say something like if the successor minus the predecessor, something goes to a non-zero real number, then we're going to get the group, hence also Z if we're over the field. What's interesting, is a curious little bit of business here, is that the additive version actually doesn't need the field structure. What's really true, and it comes up handy maybe in some other settings, but actually what we get is that in this case, if we just look at the real additive group and throw the predicate on for the range here, then this defines alpha Z. So this can be useful in some more abstract settings maybe, but the multiplicative one, because we're talking about limits, kind of seems to require also distance and multiplication and things. Okay, so what's the proof of this thing? I mean, I'll just sketch it. It's really very easy once you think about it. So sketch of proof. And it's a little bit, I think it's a little, people who aren't used to definability might find the details difficult, but I think it's pretty obvious how this is going to work now. So first of all, without loss of generality, let's just say alpha is bigger than 1. This is purely for convenience. So for all integers j, we are going to have this is just, by easy induction, over ak goes to a sub j, alpha j. I'm going to keep that a as an alpha straight. Now, what if you say, well, wait a minute, what if j is negative? Well, that's okay, because from some point on, k is going out to plus infinity. So, okay, it's just a reindexing. But so we immediately get this, right? So the group is showing up as limit points of this set A at infinity, so to speak. Okay, so if I think if I got my quantifiers and everything right, what this is going to say is that this is all the reals, such that for all epsilon, for the small, for all small, and for all big, there's something inside the range of the sequence, but also large, such that the quotient from r is less than epsilon. All right, so I think that does it. You might check my work on there. So that's the idea.
Actually, you can do that just with less than and plus. Then you get immediately that this is true just with less than and times, just because there are isomorphic via x, the two structures.
Yeah. In other words, the additive version implies the multiplicative version,
And vice versa.
and where you only need the multiplicative, where you only need the multiplication on the.
That's yeah. But just making sure, what does it mean now to say that the limit exists in just the
Less than. It's just an order or property of the order.
right? Okay. But just remember that isomorphism that we're talking about isn't definable.
Yeah.
Okay. Okay. All right. Okay. Fair enough. I didn't bother to check with that because, again, this is the more natural way to think about it, and that's how we're going to be using it. I'm leading up to eventually, by the way, eventually I'm going to make an argument that yes, even those of us who are interested only in expansions of the field of reals, there are occasionally reasons to look at the additive group as well. Occasionally. Okay, now, so this is easy, right? So nothing much here, much more difficult. And this is due to hieronymy. So I don't include that really as part of this. If alpha equal 1, so in other words, if we're in the multiplicative version, if alpha equal 1, let's see, and I think you have to say something like, and the sequence is strictly monotone or something decent. Again, I'm just trying to run off memory here. Then Z is definable.
Bounded or unbounded?
Yeah, I think it should be. I think it should be unbounded, and no, it doesn't necessarily have to be unbounded. No. This is more difficult. I mean, for those of you who are familiar with his, with the basic theorem there, if these quotients are approaching 1 nicely, then you can make an argument that you look enough like the integers that you can figure out a way to get a definable mapping from a discrete set, namely, I guess, the sequence or the range of the sequence or some variant of it. And you can map it to get a somewhere dense set, and then you have to define the integers. So, but this is definitely, this is a triviality. This is more difficult, but we're going to use it. So it's a nice thing to know about and have available. Okay, so now let's get back to work on where we were. So more on limit cycles here. We're going to do some stuff. So there's some critical issues that I keep running up against, that I have kept running up against in this enterprise. It actually is somehow more interesting to see how this happens around limit cycles than around singular points. But and it's more. I like how this works better. So I'm gonna talk my way through something here. But the same issues arise around singular points. So let's just remember. So we've been being pretty loose here. So at least, topologically, say I've got a picture like this. So I have a cycle, which is essentially a cycle of a vector of this vector field is basically a simple closed curve. The trajectory happens to be a simple closed curve. If you're thinking about these as in dynamical systems language, they're periodic orbits, things like that. But for us, geometrically, it's just a simple closed curve. Trajectories can't intersect themselves. Of course, this can look a lot more complicated, which if the complicated pictures haven't already appeared in some of these lectures, I imagine they probably will appear soon. Yes? Yeah, okay. But so these things can look worse. These can look worse, but let's just look at this. Now, what we talked about was there's, at least for analytic vector fields, there's this idea that you can't have these so-called center focuses where you have, and limit cycles, this is supposed to be isolated in the periodic orbits. But can you have it where it's can you have a center here and then it spirals in? No, not an analytic one, but I guess you could have that. There's also the notion of a one-sided limit cycle. Okay, so let's just say we're spinning into this somehow from the outside. Okay, so we're going in here, and this is a picture that we have. Now these come up in polynomial vector fields, and in which case then the other side would also go this way. So you can certainly have these things and they can show up in nice ways. Now, my cartoon here is that we can just trivially draw a transversal more or less anywhere we want. And then we can start talking about this Poincare return map again, which is doing this thing where like, then you have to consider the whole phase portrait. If you're at least for close enough here, if you're at a point, you figure out which trajectory you're on, and then you go until you come back, and that's the return map for that. So in keeping with, so we're really thinking of it as the time is coming. So this is the point, this is a point on my original trajectory, which may or may not be 0, but we're thinking of the return map as being defined on some small interval of time nearby, say. And in order to be just consistent with Perko, we'll let P denote the return map here. Now, something. Now, suppose this picture is coming out of even just C1 vector field. Is this too far out? Maybe, let's see, I'll keep it C1 vector field. That's all we need for what we're going to go. So there's a really nice test to try to figure out what's going on with the return map. It's always going to be C1 in a neighborhood of the origin, or at least on the right as far as I can tell. And this intuitively, the result is very nice. So I better keep this. Yeah, let's try to keep straight where we are here. So this is going to be the limit cycle here. Okay. Now, under any reasonable circumstances, we can parametrize this path. I mean, we know it's a trajectory, so we have to be able to parametrize it somehow. And let's say, and this is going to be a gamma at the moment, I guess. So we'll say that gamma is the image, gamma is equal to, say, gamma of some closed finite interval 0t, where this is now a solution. And so again, this is, if you were thinking about this as being a, I don't know if it complete or total flow, one of the things. If you assume that all your maximal trajectories are defined for all time, then this would be periodic with period t. So we'd start at 0, we come around here, we wind up here, and then we would just be going on like this. Okay. So there's a nice result here that even makes a lot of sense. Geometric, or in a calculus way. And I'm going to tell you what that is.
Is the sequence of time when it comes back to itself and
all of this stuff depends on the language that you want to use for flows and all these things. So any particular trajectory, if it's maximal, right? Its maximal interval of existence might be a bounded interval, but you can always you can reparametrize. So you go from minus. It's mostly for convenience, but there's some language that they use to say that if you have a flow that's everything where you're defined for all time and all these other things like that. And it makes it really convenient for talking about periodic trajectories, because otherwise then what do you mean? Well, you have to say there's some, it's not like an additive period in the normal sense of the word if it was on a bounded interval. So there's this language tend to be more called or periodic orbits, or these things like this, depending on the language of who's doing the talking. But for me, all I care about, I don't care whether it's, I'm just simply saying, I contend that I've got this closed trajectory here. I know it's a trajectory. I know it's compact. I claim I can parameterize it by a differentiable, by a solution on a closed interval. And so this is basically all I'm doing at this point. But the T would be the period if you were talking in this other language. All right, so here's this result I like. Let's give it maybe we'll give it a. So here's my original vector field F. And so what we can do, it's C1, so the divergence is going to be continuous. So it makes sense to go over here. This integral is going to exist as I integrate around here, and then I'm going to take the exponential of this thing. So what is the integral measuring? It's measuring, we're going along and checking the divergence at each point, right? Which is, so the instantaneous expansion or contraction of the vector field. So now we're going to go around and basically compute the net of this inflow outflow stuff along this curve. Now it sort of does stand to reason that if this outflow, if the net outflow is, if this is negative, so in other words, this is less than 1, but if this is negative, then you should be sucking things into you, right? So the trajectory should be coming in. And if it's positive, it should be going out. This is this phenomenon of stability that people care about a lot in vector field theory, but I don't so much because we're not doing physics. We're just thinking about the pictures. Still, so the nice thing here is that the derivative of the Poincare return map at 0, meaning where it's coming down to there, is equal to alpha. So the derivative is the exponential of the net accumulation of the divergence along the curve. Right, so again, so what we're really talking about, so what is P prime 0? P prime 0 is the instantaneous rate of change of the return map when I'm coming down. So it turns out to be this, which means that if this guy is not 0, then this is not going to be 1. And if I have that trajectory, then the intersection with the transversal as I come in is going to be a sequence that really looks like basically alpha k or minus k, depending. Okay, so if I have this trajectory, then it's these intersection points are coming in a way that I can use asymptotic expansion of groups on it to conclude that this alpha z is definable. So, and of course, if it's 0, then it's 1, so we don't know anything. But so we can say by asymptotic extraction of groups, alpha z is definable over R from the spiraling, from the trajectory that spirals in from gamma. That's right. No. Gamma is not. Gamma is the cycle from the spiral. So I mean, sure, you could think, well, spiral, it doesn't have to go around a point, it can go around circles. Pretty easy to actually just write down equations that give these things to you.
What is known about the differentiability of the Poincare method? Real analytic. Why can you write it in prime?
Oh, here it's.
Huh?
What are you assuming?
Just C1.
Oh,
Just C1. Now, actually, this is an interesting question, and I wish I knew. I actually don't know enough history on this. But so remember, when we're at an isolated singular point, the analyticity of the return map was a big deal, right? This is the Stulak's theorem. But apparently, in this setting, it's not a big deal because you've blown your singularity up to an event horizon or something, if you like. And apparently, in this setting, analyticity of it in an analytic vector field is due to Poincare from the late 1800s or something. So it's probably fair. Do you know about this?
yeah.
Yeah, it's fairly straightforward.
Yes.
But
Right on the other side, it's the same thing.
Yes, on the other side, it's the same thing when you have an analytic vector field. So it extends and yeah. So it's actually these results. So in other words, understanding the return map around a limit cycle is actually kind of easier than understanding it at a singular point.
Yeah, because the entire flow near the limit side.
Yes.
is analytic.
Yes, if you had an analytic vector
I'm
field.
confused. I thought that we are talking about the C1 vector field.
We are right now.
And you're talking about analytic things. I mean, the return map for a C1 vector field surely is not going to be analytic.
No. But it's differentiable. I'm just saying, like, I'm not claiming that this result automatically gives Poincare's result. I'm only pointing out that historically, the result about return maps in the analytic setting came first for coming into a limit cycle. It's easier to deal with apparently than going into a singular point.
Yeah, it is. because
Yeah.
again,
You can see what's going
the
on.
limit cycle, there's no singularity. So you have a neighborhood around which everything is C1. So the flow of the vector field is C1 by ODE. And if the flow is C1, then so is the.
So is the, yeah. And then the differentiability class is preserved by these arguments. I actually like to, okay, one of my crash and burn observations. It makes complete sense actually that you should be able to deal with this easier than the point because, and this is why I guess why we have to do so much work on resolution of singularities. If all you know is that you're at a point where you're zero, you can't see inside that hole to see what's going on, right? So this is like the event horizon of the black hole or something. If you could stay on the outside, you might be able to look inside and see, what am I up against? But of course, if you're already sucked down, then you're all toast. So yeah, this thing is just carrying a lot more information than a single point. But you could still use the same reasoning if you had a singular point and the divergence was not zero. That's going to mean something about, then certainly the linear part can't be zero. And then you can start busting up things into eigenvalues and all these other things and use some of these classic techniques that say, well, okay, I can use the linear part to approximate, what my local behavior is. But if you were zero, if your linear part is zero, then you need certainly more sophisticated techniques. Okay. All right, now, okay, so in this case, so if this is not zero, then alpha is not going to be 1, which means my alpha z is not just going to be the trivial group. I'm going to have one of these nice non-trivial cyclic multiplicative groups. It's there. If I'm then if I then also have this global assumption, if I then also have restricted exp and restricted sign, then I get to recover the whole spiral, right? So now I've got this, and if I'm making this assumption that I'm always working over the reals with restricted elementary functions, then I will recover a log spiral that an actual log spiral that has the same, that's basically, if I could straighten this out into a circle of a certain place, then I would have that log spiral coming in. Okay, so from this picture, I can define a log spiral, which then it's also then easy to push it out around a circle, definably. So that's there. Now, here's where the real big problem, here's where I think the really sophisticated issue is. That's great. So now we're talking about, say, we know I can always throw this, if I'm starting with something O minimal, I can always throw this thing on and preserve O minimality because it's compact trajectory. But where are we going to preserve field of exponents? Now we're back to completely not knowing anything about it. So you might think, well, okay, maybe I should make some other reasonable assumptions about compact trajectories not being able to really change the nature of the O minimal structure very much. But so then here's one trajectory, and then here's another. And so we're going to try to throw that onto the structure. And where is this going to wind up in our classification result? Well, it's certainly possible that there could be other stuff going on elsewhere where you're going to now define the integers. That's certainly possible. But if that doesn't happen, I want to be able to say, now maybe, see, that's the thing. Maybe I can't actually recover this particular trajectory from the right log spiral definably. Maybe I can't do this. In fact, I know examples where we can't do it. You'd need some restricted analytic functions in order to do that. So the real issue is whether I can recover this thing from gamma, from the cycle, and from the log spiral that's going into it. Because then I would get to say something, because I want to be able to say, all right, fine. If I throw the cycle in, then I'm not going to mess with the field of exponents. We know we're not going to have a problem with the O minimality. And so far, the only model we have for understandable non-O minimal tameness is when we take O minimal, field of exponents Q, add a log spiral, and hope that we're in there. So that's what we want. We want to be able to say that if I throw this spiraling object in and I don't define the integers, which is definitely possible because you have all kinds of other definable function sets running around, but if we don't define the integers, I want to find a way to straighten out this picture, at least in a compact neighborhood, because remember, we really only care about the germ here. I want to be able to straighten this out by something that when I throw that on, I preserve O minimality and the field of exponents. And we don't know how to do this yet. We do in the analytic thing, there's this, I mentioned this, there's this, if you have an analytic vector field at an isolated singular point and its linear part is, well, okay, linearly conjugate with this F omega, then you're definitely going to have a spiral. And in fact, in that case, there is an analytic transformation of the origin that takes the trajectory to the appropriate log spiral. So if we're in R sub n, then we can always reconstruct the trajectory from the log spiral that it looks like. So we've got one direction here, right? This thing is going to wind up looking something like a log spiral, except it's around a circle now instead of the origin. Great, so we know that, but a real question is how can I get this, can I reconstruct this guy from the log spiral? And so this is like a big obstruction at the moment, and it seems like it should be true, but we don't have proofs for these things yet. Now, so let me just mention one more thing. Now, what if this guy's 0? So then the alpha is 1. So now, instead of AEG, I can use Hieronymus' extension of this to then conclude that I'm coming in pretty much like the identity. So this is something called tangent to the identity. So that actually does mean that I have to be bunching up and then you define the integers. So we actually have better theorem for when we're dealing around a limit cycle. So in this case, either from the intersection of the trajectory with the positive real axis, I'm either going to define the integers, in which case we're over, or we're going to define some cyclic multiplicative group, and then we're going to get the log spiral because we're assuming that we have restricted exponent, restricted sign. So I think it's interesting that, well, does that remind you of anyone? Wait. Okay, I'm ending now actually, but I just I think it's very interesting how you know, when you first think about it, you think, oh, it should be much worse to try to figure out what's going on around these limit cycles. But in fact, now you have extra information, there's more room going on. And in fact, there are sort of better theorems. But it doesn't change the fact that we still, this business of how to straighten things out definably, that's an issue that we haven't been able to solve yet. Right?
But if I understood you right, you're saying that if you have if the vector field is analytic, then you can do this? Yes. Because of working in R sub n, you can do an analytic transformation so that
Around the cycle, I don't know, but
I think you can collapse it to a single. You can collapse it maybe.
is that analytic?
We're not sure. Okay, granted, not sure. So we do know that if we're at a singular point and spiraling in, then for sure you have an analytic transformation that does the job.
okay.
If the linear, well, more than that, right? There's all that stuff about eigenvalues and all that. But if the linear part looks like an F omega up to you know, then for sure.
Okay. Situation is more complicated.
Yeah, so in some sense you have better information, but now maybe we have worse information. I guess I should.
Well, yeah, but the collapsing of gamma is a point that's not at the point.
No, it won't be analytic at the origin anymore. So
I see.
So to use that kind of argument, you would have to show that you can integrate the vector field around the entire limit cycle in a way that repeats the same, let's do the same, changes the spiral.
Okay.
which, by the way, what brings me. Oh, I'm over time. I'm sorry. The closing remark. Once again, we're back to this thing where my current slogan is that almost every interesting open problem about minimal analytic geometry somehow boils down to the fact that we don't know how to integrate with respect to parameters. One way or another, we still don't know how to integrate with respect to parameters in wide generality, right? In some very special cases we do. But yeah, Yeah, sure. Let's just integrate the vector field and throw it. No. Yeah, we don't know how to do that. We really don't understand
We don't
what
know how
happens.
to do it all minimally.
Yeah, whether you can do it all minimally. This
Okay.
is still wide open, except in some very special cases. Sorry. Ah, so this, oh, see, so there we go. Something new to be checked. Maybe we can. Yeah, we should take a look at that. Maybe for the analytic case, the cycle is also in that case. Maybe we also have the result. Okay, sorry I went a little over, but I got a little enthusiastic there. Thanks. I'll be back Friday after next.
Locally, you look around here.
Yes.
Can you move this locally analytically to maybe